because 2 days before my flight, I slightly injured my left eye, and I have to take some treatment, medical. But I'm happy, nevertheless, to make an online talk on this remarkable conference. And I want to say that I'm happy to be one of the students of Viktor Matveyevich. My talk will consist of 3 parts. Parts 1 and 3 are devoted to my own recent results, and part 2 is based on our recent joint work with Anton Eisenberg. And here we have a convention that the Boolean group Z2 to the power n we call a real torus. The torus Tn, a complex torus is just a compact torus, the product of circles, and Spn, Sp1 to the power n, a quaternionic torus. Here we're coherent with Arnold's ideology regarding the twin real complex quaternionic. The first part, the so-called doubling construction. Just take some pairs, a house of closed pairs of spaces, at least 2 of them, with non-degeneracy condition that AI are not empty and doesn't coincide with the whole space Xi. Then for any such a pair, we may consider a doubling of this pair. It's just you take 2 mirror copies of this pair, Xi plus AI plus and Xi minus AI minus, and this is the mirror, and glue them by the identity map on the mirror. Just an example, if you take the doubling of the disk is just a sphere, and you may take in mind that you have here some manifolds, compact or non-compact, but with non-empty boundaries, and these are the boundaries of these manifolds. Then the doublings of these manifolds is just usual doublings in manifold theory. And for any doubling, we have the canonical involution that permutes the mirror copies of this Xi, and it is identity on the mirror. So if you take the direct product of these doublings, you have the component-wise action of a real torus. Each involution acts on each of these doublings. Sorry. And you have the subgroup GK in Z2 to the power k of index 2 consisting of even subsets of involutions. So it is isomorphic to Z2 to the power k minus 1, and set just the boundary of the product of the pairs as it is usually done by this way, when the boundary is just the number of the points that some point is putting in some AI. And the first theorem is just that if you take this product of doublings and take the quotient space by the group GK, then it is again a doubling of this space. And so what we have as a corollary, just a topological corollary, you may take as the doublings, you may take the spheres standard spheres, and the involutions are just the standard involutions that permute the north and the south pole of the sphere. And then you have the product of spheres and commuting involutions acting on this manifold. And if you take the subgroup GK of index 2 consisting of orientation preserving elements, then you will have this homeomorphism, that this space, this quotient space, is homeomorphic to the sphere, to a genuine sphere, and it's just a corollary of this result. You have doubling of the disks, and this is again a disk, and its boundary is again a sphere. So this doubling is again a sphere. But what is more interesting, that in this setting, these spheres are just round spheres, and in coordinates we may write the following explicit formula. The canonical projection onto the space of orbits is given by this formula. You just take the coordinates on this space or the spheres, throw away the last ones, concatenate the first ones, yes, and the last ones you just take the product, and you have the vector with the m+1 coordinates, which is non-zero always. And if you want to have a length 1, just norm it by its Euclidean norm. And moreover, the resulting branch covering of this type is globally C omega smooth and non-degenerate at the point of local homeomorphism. So not degenerate means it is a local diffeomorphism at any point of local homeomorphism. Then I want to say that in the case k is equal to 2, when you have two spheres, yes, and one involution, this theorem with this formula was already proved in the PhD thesis by Christophoros Neophytis in 2014, and I know it only about a month ago. This is a young topologist from München University. What we want to say that here we have k-1 involutions acting on this product of k spheres such that the quotient space is a sphere. And k-1 is the sharp number, the sharpness of this number. Recall that the rational cup length of a topological space is the maximum number m over homogeneous rational cohomology classes, here of degrees at least 1, with non-zero cup product. And here's the theorem. Then for any effective action of m commuting involutions on oriented closed connected manifold XD, which preserves orientation, then for Czech cohomology of the orbit space, there is an estimate that the cup length of the orbit space is greater than or equal than L of x over m+1. And if the orbit space is a topological manifold, then we have the classical Bernstein-Edmonds estimate that says only this one estimate. And this is more simple to prove because Bernstein-Edmonds, they treated the general case of arbitrary branch coverings between oriented manifolds. But we have here the very, very particular case when we have m commuting involutions on any manifold. But this estimate is much more easy to prove than the estimate of the Bernstein-Edmonds, but it is more stronger, of course. So if you have here k and m is equal to k minus 2, we have a corollary that if we take any action of k minus 2 commuting involutions on the product of k spheres, which preserves orientation, then the rational coupled length of the orbit space will be at least 2. So it could not be a rational homologous sphere. This is the part 1. Part 2. Some generalization to the complex torus. So consider k spheres of dimension at least 2. I will write them in this form. So you have a real vector and the one complex number and the standard relation. And you have k of them. And again, consider the direct product of these spheres. It carries a left smooth action of the complex torus tk minus 1. Namely, the element of this group translates a point to these points. So xi's just are the same, but these complex numbers are rotated in this way. And our theorem with Anton states that the quotient space, again, we have the product of spheres and the quotient by the action of this specific action of tk minus 1 is homeomorphic again to the sphere Sm, but of course dimension is not equal to the dimension of this manifold, is equal to the dimension of the manifold minus k minus 1. And again, the canonical projection onto the orbit space is given by the formula. You need to take the xi's and the last ones, z1, z2, and zk, you just multiply. You get a vector and just norm it in the Euclidean norm. Okay. And quaternionic analog. You have k spheres of dimension at least 4, and again we write them as just xi and qi, where qi is quaternions and subject to this relation. So it is again a round sphere, and we again consider the product, and it carries a left smooth action of the quaternionic torus of rank k minus 1, this torus, and the rotations, quaternionic rotations, translates this point to this point, just as in the complex case. It's not too hard to prove that it is a left smooth action. So xi are the same, but the quaternions are rotated by these formulas. And again, we have the sphere as a quotient space. Its dimension is equal to this, and the canonical projection of the space is again this formula. So a little bit to tell about how to prove this. Here, when you just gained this formula, then the whole proof is just the analysis of the first year, and at one time, the first time you prove that the canonical projection may be given by the formula without this denominator, and then you prove that you can also take this denominator, and it is proved that this map is a projection between this space and SM. Okay. But here we have a very interesting problem. As I said previously, if you here we have, when we have the real torus, this number k-1 is sharp. So if you take k-2 commuting evolutions, then you never can get a rational homology sphere. We may pose the analogous question in the setting of this one, this complex torus and quaternionic torus. And this is the problem. So is it true that for any arbitrary smooth effective action of the complex torus TR, where R is from 1 to k-2, or the product of k spheres of dimension at least 2, the corresponding orbit space is not a rational homology sphere? I think it is so, but it seems very hard to prove. I discussed it with Anton and with Taras, and there are no easy steps, easy decisions in this problem. And is it true also that for any arbitrary smooth effective action of the quaternionic torus SP1 to the power R, where R is again from 1 to k-2, on the product of k spheres of dimensions at least 4, the corresponding space is not a rational homology sphere? So it is not trivial even in the simplest case where R is equal to 1. So you have, for example, 3 spheres and the circle action. You may ask, is there some action of a circle on the product of 3 spheres such that the quotient space will be a sphere or a rational homology sphere? And it is a very interesting problem. Okay. And some generalization of these two formulas. Consider non-empty compact Hausdorff spaces x1, x2, xk, and an arbitrary compact Hausdorff group G. You may just take any compact Lie group G and compact polyhedrons, simplicial complexes x1, x2, xk, and consider the following left continuous action of the group G to the power k-1 on the product of joins, namely the rotation elements translates a point where you have the first join. You have a point from here, x1, the point from here, q1, and barycentric coordinates 1 minus t1, t1, and etc. in the second join, in the third join, and the cath join, and you send this point to the point x1 q1 r minus 1 x2, and you just take the same t1, t2, and tk, and just rotate the coordinates from here. And it can be proved, not very hard, that the orbit space of this protocol of joins quotient by this any group G is again homomorphic to the big join x1 join x2 join xk join G. And the canonical projection onto the space of orbits is given by this formula. Here we take again the last the q's, you multiply them and take the barocentric coordinate here, the product of the corresponding barocentric coordinates, but you just need to normalize it by normalizing factor in order to have the sum of the coefficients equals to 1. And let us show some trivial but not very trivial corollary. Take the G, just the trivial group. Then it's a point, and any join is a cone. So here is a cone times cone times cone, and you factorized by the trivial group, so you does not factorize. You do not factorize, and this is homeomorphic to this join, and this join is the join of xk, x2, x1, x2, xk, and the cone of them. This is a standard topological fact. And what I want to say is that the topological part of theorems 2, 4, and 5, when you have the real torus action on the product of spheres, the complex torus action on the product of spheres, and quaternionic torus actions on the product of spheres, the topological part is just the special case of this general theorem, where you take the G, the real torus, the complex torus, and quaternionic torus respectively, and xi the spheres of the arbitrary dimensions. But what is more interesting that when you have this formula, for example, you have this very beautiful and explicit formula in coordinates, and this is the most interesting part of these theorems. Okay. And part 3, I want to tell you some new results of actions of finite groups of odd order on manifolds. So if you have, for example, any group G that smoothly acts on some smooth manifold, such that the orbit space is again a manifold, then for an arbitrary group G, it is a very difficult problem to say something about this. But you have two poles, maybe, when G is just the Boolean group, then some number of commuting evolutions on the one hand, and then on another hand you have any group G of odd order. First of all, I want to say some classical theorem about group transfer. Consider any paracompact G space X for any finite group G, and let K is be a field of coefficients with characteristics equal to 0, or P such that P doesn't divide the order of G. Then, if you have this canonical projection onto the orbit space, this is automatically paracompact. Then for Čech cohomology, the induced homomorphism is always a monomorphism. And its image is the full subalgebra of G invariance here. So you have an action of G of X, so it acts also on the Čech cohomology, and so here is this subalgebra of invariance. Okay. And now take any connected, not necessarily orientable topological manifold XD. Suppose we have some finite group G of odd order which acts effectively on G, such that the orbital space is again a topological manifold. We want to have this theorem, but this theorem treats with Čech cohomology. But for topological manifolds and moreover for inner spaces, Čech cohomology coincides with singular cohomology canonically. And now take K is Z2. So G is of odd order and K is Z2 coefficients. Then the canonical projection, we have that this ring is just the ring of invariance here. If you have a topological manifold, it can have some smoothings sometimes. For any smoothing, you may consider a tangent bundle and its Stiefel-Whitney classes and Wu classes. But as we know, the Stiefel-Whitney classes are homotopy invariant. So for any smoothing and for identity map, they are mapped onto each other. So we may take topological tangent Stiefel-Whitney classes of these manifolds and topological Wu classes of these manifolds. And there is a classical formula that if you have the total standard square of the total Wu class, you get the total Stiefel-Whitney class. Here is the definition of the Wu classes of topological manifold M. And there is this is the theorem that in this setting the Wu and Stiefel classes are invariant in this setting, namely the following holds. This map is not only the monomorphism that such that this is a subalgebra of invariance. It maps the Wu and Stiefel classes to the Wu and Stiefel classes of X. So the Wu classes and Stiefel classes are mapped to them. So as a corollary, we know that the boundary, the compact connected manifold, topological, even topological, is a boundary, maybe a boundary of unoriented manifold, if and only if all Stiefel-Whitney numbers are zeros. And then zeros are mapped to the zeros, of course. And we have this corollary that this manifold is a boundary if and only if this quotient is a boundary. And here I want to pose the following interesting problem. Suppose both manifolds are smoothable and orientable. Is it true that in this setting, rational point-trading classes are also invariant, namely, they are mapped onto each other? So P1 is mapped to P1 of X, P2 of Y is mapped onto P2 of X, etc. And for free G actions, it's really true because you have non-branching locus. You have just ordinary genuine covering space and modular as celebrated Sergei Petrovich Novikov theorem about topological invariance of rational functional classes, you will have this property. But for non-free G actions, it's absolutely unevident why it is so. I haven't constructed any contradiction here, counterexample, but I have some examples where it is so. This problem seems very hard, but take just a more easier problem 2 prime. Take a smooth non-free action of a cyclic group ZP, P is greater than 2, on a smooth orientable closed connected manifold such that every component of a fixed point set is a submanifold of a real codimension 2. This is equivalent here in this setting that the orbit space will be a manifold. So is it true that in the setting the rational quadratic classes are also invariant? A more simple version, problem 2 primes. Take a smooth non-free action of a cyclic group ZP on a smooth orientable closed connected manifold of the dimension 4m, such that every connected component of a fixed point set is a submanifold of real codimension 2. Is it true that the signature of the covering space is just the signature of the base manifold times P? So from Hinsebruch formula, it is to be so if the previous problem is true. So this question is open, still open, even for four-dimensional manifolds. So, well, of course, the first time when you have point-tracking classes is dimension 4, and here we have only signature, because the first class pi1 is just 3 signatures. Even in this setting, I have no any contradiction, and I have no any proof of this formula. And why it doesn't work with p equals to 2? There is a celebrated Kuiper-Massey theorem such that if you take CP2 and take one involution, just conjugate all coordinates here, homogeneous coordinates, then you get S4. And of course, here Von-Schragen classes is 0, and here we have 0, but here we have 1, because the signature of CP2 is 1. So it is not true. And again, for my formula that the Stiefel-Whitney class is mapping to the Stiefel-Whitney class, again, it is not true because the Stiefel-Whitney class is not 0. The second Stiefel-Whitney class of CP2 is not 0. But here we have 0. So a simple corollary from problem 2. If you have this equality and P is just an odd prime number, then of course you have this equality. The signature of the covering manifold is equal to the signature of the base manifold modulo 2. Or equivalently, the middle Betti number of this manifold is equal to the middle Betti number of this manifold mod 2. And here I have just a purely algebraic lemma in representation theorem. It has many proofs, but all proofs I know, they use the celebrated Fate-Thompson theorem that any odd group is solvable. And I don't know any proof of this lemma that doesn't use the Fate-Thompson theorem. So for any representation of any finite group G of odd order in GLV, where V is a finite dimensional vector space over the field K, where K is between Q and R, the following quality holds: have the dimension of the whole space, vector space V, is equal to the dimension of the invariant subspace, modulo 2. So here it is because of a transfer dim over Q of some space here to the power G. So this is just this equality. So this corollary is true, but the proof of but the problem 2 prime, this problem is still an open question. Okay, so here are some references. This is our recent arXiv preprint where we proves the complex and quaternionic analogs of my theorem about the quotients of spheres, products of spheres by tori. And here is my 2 papers. In this one, I introduced the doubling construction and proved the theorem for the real torus. And in this one, I proved the formula, the estimate the sharpness of the number of commuting evolutions. So I have, maybe I will stop here. So thank you for your attention.
Yes, thank you very much. Please, questions, comments, just remarks, maybe.
Yeah, may I ask one, if possible? This is Vanya.
Okay, okay.
Hi, Mitya. Hi. Thank you
Hi.
very much for your wonderful presentation. It's really inspiring. I have a question about one of the first conjectures or open questions regarding the product of spheres and the torus action. So my question is, perhaps you can apply the results of Viktor Matveyevich and Taras Evgenievich about partial quotients, as well as some recent works of Matthias Franz, who actually computed ordinary cohomology of partial quotients of moment angle complexes by the actions of coordinate tori. And perhaps when the dimensions of your spheres are odd, it means that the product is the moment angle complex corresponding to product of simplices. And perhaps you know the answer what homology of this partial quotient is, and then you can simply compare it to the homology of sphere and you are done, let's say. What do you think about that?
Okay, thank you very much, Vanya. But you take these numbers odd, and you take not an arbitrary smooth action, but some action from moment angle complex theory, partial quotient. Yes.
Yeah, some coordinate some coordinate subtorus, let's say. Yeah.
And so
it can be an arbitrary subtorus in the torus T to the power K. Well, actually, T to the power M, where M is the number of faces of the polytope, the product of simplices. So you can compute what it is. So there is a big, very big compact torus, and you can actually compute this partial quotient homology with respect to any subgroup of this big torus. So I'm not saying that I have an answer to this conjecture, but all what I want to say is just perhaps their results can give something, at least in partial case, in some particular case.
Okay.
Your problem.
Okay.
Yeah.
Okay,
But of course, it's not complete solution. Of course, even in the case of odd MI, I'm not claiming that it's complete solution, but in partial case, in particular case, perhaps it can give an answer.
Okay,
That's
okay.
what I'm saying.
Thank you, Vanya. I will check this. So,
More questions? If there are some. Okay, thank you very much for your talk and for calculations. So we finish this session, and now we have a lunch time, and we meet in 2:30.